I'd like to introduce tonight's speaker. Our guest speaker is Dr. Niv Drory. Dr. Drory was born in Israel, obtained a PhD in physics at the University of Munich, Germany, writing his thesis on the first wide-field near-infrared survey of distant galaxies. He came to Texas for the first time as a Humboldt Fellow in 2002, where he joined the early work on the Hobby Eberly Telescope Dark Energy Experiment. So that's the HETDEX experiment that you might have heard of if you've been to some of these meetings in the past. Dr. Drory has been a research staff member of the Max-Planck Institute for Extraterrestrial Physics, MPE, and spent 2 years as a professor of astronomy at the National Autonomous University of Mexico. He's interested in galaxies, cosmology, and instrumentation. He returned to Texas in 2013 to work on the HET wide field upgrade and HETDEX, and is now a senior research scientist at McDonald Observatory. He is also deeply involved in the Sloan Digital Sky Survey, the Sloan DSS, as an instrument scientist for MaNGA in SDSS-IV and PI for the local volume mapper in SDSS-V. So without further ado, I'd like to welcome Dr. Drory to our meeting tonight. Dr. Drory, thank you so much for joining us.
Thanks, Joe, for the very generous introduction. It's a pleasure to be here.
Let me go ahead and stop the share here. And while you're bringing up your presentation, I just wanted to remind folks that if you did have questions for Dr. Drory as we get to the end of his talk, please feel free to add those to the chat feature that we have in Zoom, and we'll get to those in the order in which they're asked. I will also ask other folks, if you wouldn't mind muting your microphones so that we don't have any disruptions or accidental echoes, things like that, that would be much appreciated. Thank you.
All right. Can you all hear me well?
We can. Thank you.
Good. All right. So it looks like my mouse pointer does not move. So I'll try to describe what if I'm referring to particular features on the slide, and if I don't, just stop me and ask, please. All right. So I'm going to talk about cosmology in very broad terms, and in particular how cosmology became a precision science and what the hard evidence is by which we think we know what we know. And I will stick to very basic observations about cosmology. And towards the end of the talk, we'll get to a bit more early universe features, perhaps have a word or two about inflation and things like that, but I'm not going to concentrate on those features in this particular presentation. But if you have any questions, please don't hesitate to ask. And I think what we'll do is we'll collect the questions and do a question and answer session at the end, right, Joe?
That is correct.
Yeah. Okay, good. So let's start with a very brief history of the subject. And that is essentially, essentially every culture has developed some sort of mythological or religious cosmogony and some cosmology as well, i.e. stories of the origin of themselves, of humanity as a whole, and of what they consider to be the world, the universe, everything they know to exist. So it's essentially a very ancient and deeply rooted human endeavor. The scientific study of cosmology, with the Western definition of scientific study here, really went through 3 paradigm shifts over its history. In the antiquity, we were convinced that we are living in a static, unchanging, and hence infinite, in time at least, universe with Earth at its center. And also different laws govern what happens on the Earth and what happens in the heavens. At the beginning of the modern era, the sun moved to the center, and something even more important happened, and that is the realization that the same set of physical laws actually govern the Earth and the heavens, and there is actually no real distinction between the two of them. And in the 20th century, then, the perhaps most relevant paradigm shift, where the universe changed from being eternal and unchanging to a dynamic, evolving universe with a beginning with the Earth, the sun, or humans playing no particular role in it, apart from being the observers who speak about it. In the past 100 years, modern cosmology developed as one of the newest branches of physics. It is essentially as old as quantum mechanics, or as young as quantum mechanics, if you want, as opposed to astronomy in general, which is perhaps the oldest branch of physics. 100 years ago or so, the only real cosmological fact that is known as in terms of an observational fact is that the night sky is dark, right? That happens to be a cosmological observation for a reason that I will come to in a moment. The first measurements of distance outside the solar system in 1837. The first distance outside the Milky Way 100 years later in 1923 by Hubble. The famous observation of a Cepheid variable in M31 that unmistakably proved that M31 is outside of the Milky Way. About 50 years ago, the Big Bang conjecture, but very little evidence at that point. This was a theoretical concept based on general relativity alone. 25 years ago, we're moving towards a lot more evidence for indeed a Big Bang type universe governed by general relativity, but no accuracy whatsoever in determining the parameters of this universe. I.e., when I was a student, we still basically had, the Hubble constant was known only to within a factor of 2, and omega matter had essentially a 100% error on it. We could have been living in a universe that is essentially empty or omega matter equal 1, which is what the theorist wanted, but there was no measurement of that whatsoever. I remember actually giving a talk in front of a bunch of physicists early on in my career, where I argued that from data of distant galaxy clusters, you could see that omega had to be smaller than 1, and they were all very flustered about that. And today, we have a standard model of cosmology with about 6 or 7 parameters that are all determined at percent level accuracy. So this field has gone through an enormous development in the past half century or so, from essentially being a conjecture-driven endeavor to a field of empirical study. So, but it's a funny science because we actually cannot do experiments on the universe. You may consider that actually a good thing, that we can't do that. But we can't just fiddle with parameters and see what happens in the lab like we can do with many other aspects of physics or other sciences. We also can't make universes in the lab. Again, that might be a good thing. But we certainly can observe what the universe is like, and we can study what past, present, and future conditions of the universe are compatible with, and which of those theories of ours are compatible with these observations that we make and with what we know about laboratory physics. So the one statement that governs essentially everything in modern cosmology is that there is only positive mass, right? And so there is no negative gravitational charge. There is only positive gravitational charge. And so gravity, in contrast to electromagnetism, cannot be shielded. And therefore, gravity is the only relevant force on large scales. It will always eventually dominate. General relativity is the physics of gravity. That's the theory that describes how gravity works. And so in that sense, modern cosmology arguably began with the invention of general relativity by Einstein in 1916, where he published the first paper on the subject. Okay, so let's get back to our first cosmological observations. The night sky is dark. Now, this was basically the only thing that Einstein could say he knows observationally about the universe, that the night sky is dark. And at that point in time, people thought the universe is static. It doesn't change, and hence infinite. It has to be. And so if the universe were infinite, then for any given sightline, you eventually hit the surface of a star. In particular, if the universe is also unchanging. The night sky would then be as bright as the sun because surface brightness is conserved in such a scenario. Okay, so eventually you just hit something that is as bright as a star, no matter where you look like. And that is a fact that was actually known in the 17th century already. Kepler noted that, Halley noted that in the 18th century, and many other people since. And it's become known as Albus Paradox, because obviously the night sky isn't as bright as the surface of the sun. Okay, and here's just a little illustration of how that works. If you fill up space with stars at random distances, eventually this is what happens. You end up with the surface uniformly illuminated, and it is as bright as the average star. And the sun is a very good average star. Now, general relativity changes that, and the way it does so is by it simply does not allow stable static universes. By the way, this is one of the Einstein's few mistakes he made, which is to not see this at the beginning, and trying to find ways whereby he could make a infinite, stable, unchanging universe using GR. And he actually managed to do so, right? That's how he introduced the cosmological constant. But the mistake that he did not see is that the universe that he created was actually unstable. A small perturbation would cause it to either immediately expand forever or contract. And he didn't notice that. And that is actually the reason why his use of the cosmological constant is not the same way we look at it today. Anyway, so in GR, if you're not making this mistake, then the universe is always either expanding or contracting. Okay, and that is indeed the first observation that we made of cosmological nature past Albus Paradox in 1929 by Edwin Hubble. Edwin Hubble was not the first one to actually measure this and plot a relation like that of velocity versus distance, but he was the first one who interpreted that as a cosmological phenomenon, i.e. as evidence for the expansion is predicted by GR, and hence we attribute this to him. But to be fair, these measurements existed and were shown in diagrams like that in the 20s before Hubble. So what he did is look at distances at galaxies in the neighborhood of the Milky Way. Those were the only ones accessible to him with the instrumentation that he had. And he noted that the further away you look, the faster a galaxy would recede from you as measured by its redshift. And this is the data from his 1929 paper. And you can see that there is clearly a relationship, but the slope of that relationship, which we call the Hubble law, is really very ill-determined. And we only go out to about 2 megaparsecs, which is about twice, maybe 2.5 times the distance to the Andromeda galaxy. So it's really very much the very local neighborhood, and hence the large scatter. About 3/4 of a century later, here's data from 1995, and now you can see that we go out to 500 megaparsecs. And Hubble's data fit into this little yellow square in the left-hand corner of the diagram. So that is an expansion by, I don't know, 2 orders of magnitude or so over Hubble's data. And now you can also see that the relation becomes a lot more clear. And there is a very defined slope to this relation, which is universal in the local universe. And we call that the Hubble constant, right? How much faster something gets if you increase the distance by some scale factor. Here is data from 2005, only 10 years after the previous data. And again, the 1995 data fits into the little yellow square at the bottom left part of this diagram. And now we're going out to gigaparsecs. So we've yet again increased the scale by a few factors of 100 or so. And you now can see that the relation is no longer strictly linear. It has curvature to it. And that is because we are now leaving the regime where we can look at the universe as not having changed over the period that we're measuring here, right? So what we're seeing here is signs of the expansion rate actually changing. Okay. So the next thing we have to look at is the universe is homogeneous and isotropic, i.e. it's basically is the same wherever we look, and it's the same in every direction. And those two are not the same statement, because on the left-hand side, you can see something that's homogeneous. It is the same everywhere, but it's not isotropic. There is a preferred direction, which is the horizontal direction in this particular case. And on the right-hand side, you can see something that's isotropic. It looks the same in every direction from the center, but it's not homogeneous. If you move away from the center, it no longer looks the same. Okay, so those two are independent statements, and the universe obeys both. It is homogeneous, looks the same everywhere, and it's isotropic. It looks the same in every direction. And here is a plot that should convince you of that. These are the locations of very distant radio galaxies. The band where there is no data is the disk of the Milky Way. This data set is collected by a radio telescope located in the northern hemisphere, and hence there is no data all the way in the south. But in any case, you can see that there is indeed, you cannot make out a preferred direction, and you cannot make out any location that is any different from any other location, with very few exceptions, which are these slightly bigger black splotches that you can see. There is two very close to the Milky Way disk and one sort of a little bit offset from the Milky Way disk, and those are very nearby galaxy clusters. But once you get past that distance, you see that there is indeed homogeneity and isotropy, and isotropy seem to be very well observed by the matter distribution in the universe. Here's another picture of the universe, and that actually is a photograph of the universe. It's not just an orange oval, and that is actually a photo of the microwave radiation. We're used to seeing a photo where you see lots of colorful splotches, but that is actually not what you would see if you just took a picture of the microwave radiation. You would see this, which is something that's uniform to one part in 100,000 or so. And so indeed, even there, where you're looking at very, very large distances and you're looking at the radio, at the microwave wavelength, you see that the universe is extremely homogeneous and extremely isotropic. Okay, however, on smaller scales, things look a little bit different. On smaller scales, the universe shows a lot of structure, and it's neither uniform nor homogeneous, right? And the density only converges towards a uniform distribution at very large distances of about a gigaparsec or so, maybe 2 gigaparsecs or something like that. And here you see an early redshift survey out to about, I don't know, 600 megaparsecs or something like that. So these are certainly cosmological distances. And you see that that these 60,000 galaxies that are plotted here are distributed in a very non-homogeneous way. They are clamped together, and there's sort of linear structures here. And by the way, the reason why this sort of tapers out towards the edge is simply because the survey becomes more incomplete as you go towards the edge. i.e., it catches only the brightest objects far away, rather than all of them. And so you see that effect in the data here. But this distribution is very far from homogeneous. But if you go further out, here we have increased the distance we're looking at by a factor of 4 or something like that, between 3 and 4. We're now plotting 140,000 galaxies. You can see that you're starting to see things smooth out, and the density field becoming more and more uniform on average as you move away. Okay, so we've observed an expansion, and it means that the universe must have been smaller, denser, and hotter in the past. Okay, and the point here is that this is very often presented as an extrapolation from Hubble's law, but in fact it isn't, because we can observe that relation directly by looking at the temperature of the microwave background, which we can get by measuring the scattering of electrons in galaxy clusters off of the microwave background photons. And that scattering gives us a temperature. We can measure directly the temperature of the microwave background photons. As we look back in time, we find galaxy clusters further and further away. And here time now goes from right to left. We are sitting all the way on the left of this diagram where the green star is. And if you start looking further and further away or back in time, you can see that the temperature increases very uniformly. And the data get a bit rattier as you move further away. But nevertheless, this is a very convincing diagram that shows that the universe indeed was denser and hotter in the past. And this relationship is directly proportional to 1 plus redshift if you were to actually look what the relationship is. And it is exactly what you expect, the microwave background to do. Okay. So the universe began in a hot and dense state. So early on, at some point, if you just continue going, it must have been too hot and too dense to be transparent to light. And that happens when hydrogen gets ionized, i.e. when the temperature is about 10,000 degrees. Hydrogen loses its electron and becomes an ion, which is simply a proton and a free electron. And the free electrons couple very strongly to light, to photons, via Compton scattering. Okay, so basically they play billiards with each other. The electrons and the photons just bump into each other and scatter. And it's pretty much like billiard balls do, more or less. And so before that point in time, right? You are basically looking into something that is opaque to you because light bounces around all the time and cannot travel large distances like it can today, allowing you to see distant features in the universe. Okay, so back then, before hydrogen becomes neutral, you cannot see very far in the universe. Light is not a good measure of what's going on. Okay, but once it becomes transparent, light can travel freely, and we should be able to see what's going on. In particular, we should also be able to see the radiation field as it existed the moment the universe became transparent. Okay, and that is because at that moment, photons suddenly become free to stream as far as they want, right? There's nothing for them to interact anymore. All the electrons are gone. They are bound to hydrogen atoms at this point. And so there should be a radiation field, if our prediction is correct, that encodes the state of the universe, the density or temperature field of the universe at the moment when it becomes transparent, and that is about 300,000 years after the Big Bang. Okay, and so here's basically what we are thinking on the left-hand side. So time runs from left to right in this diagram, and we start with a plasma consisting of electrons, protons, and our yellow photons, which are now everywhere. They scatter all the way around. There's nothing to see. Everything is opaque. And at some point, there is a relatively sharp transition. The temperature falls below the ionization energy of hydrogen, and our electrons get bound. They no longer interact with the photons, and our photons are free to stream wherever they want. Okay, and that boundary is sort of roughly here in this particular diagram. Okay, so Gamow was the first one in 46 to make this prediction. And it was then discovered about 20 years later by Penzias and Wilson in a happy accident, one of the happiest accidents in modern cosmology. And at the same time, this is also the end of our road in terms of what we can discover by looking at light. Okay, so we are looking at the density field as encoded by these photons. And the density field is non-uniform today. So these non-uniformities must have existed at some point, right? If something is completely uniform, it will not become non-uniform by itself. There has to be some non-uniformity seated in this. And indeed, so this density field should reflect that. And that was confirmed in 1992 by the COBE satellite, for which people got the Nobel Prize later. Penzias and Wilson, by the way, also got the Nobel Prize eventually. And found the predicted fluctuations. So before COBE, this is exactly the picture of the microwave background we had at that point. And this is what COBE saw. And these are indeed density fluctuations of the order 10 to the minus 5. Now, COBE could only see the fluctuations on very, very large scales. About 20 years later, here's what WMAP saw. That is the next iteration of satellites experiments that looked at the microwave background. And yet again, 10 years later, this is the current state of affairs, at least in terms of observations from space. This is what Planck has seen. And if you look very closely, I'm going to go back for a second. Look, for example, at the cold spot roughly in the, so the blue area, the big blue area roughly in the center of the image. And then there's a sort of a reddish area further to the right. And if you go forward, you can already see the cold spot here and the hotter area to the right. And you see it here again, the colder area and the hotter area to the right. And it's preserved in the Planck data as well, which basically shows you that the previous generations of data were actually very reliable. They simply did not see the full picture because they were limited in resolution, but the data themselves are extremely good. Okay, so if we have a plasma with some density fluctuations in it, then we'll also get sound waves in this plasma. These density fluctuations, when they form, they will lead to waves propagating through this plasma. And the properties of these particular density waves can actually be calculated and predicted. And the reason for that is because this plasma early on is relativistic. Our electrons and our photons form what's called a relativistic plasma, and relativistic plasmas are, lucky for us, very, very simple things. They're actually not more complicated than classical plasmas. They're a lot simpler than classical plasmas, and that is because the sound speed in these structures is fixed, and it's exactly the speed of light divided by 3. So it happens. And so we know the propagation speed of these waves. And also from what I've just said, you can also deduce that there is no dispersion relation in these in this plasma. All waves of all wavelengths propagate at the same speed. Okay. So what is the largest wave we can build in this particular plasma until it becomes visible in the microwave background? Well, how far can a wave go from the Big Bang until 300,000 years after the Big Bang, when the microwave background decouples? Well, that is just, 300,000 years divided by the speed of sound, i.e. The speed of light divided by 3. And it happens to be 143 plus minus 2 megaparsecs, okay? And these plus minus 2, they come from small uncertainties of exactly what else is in this plasma besides photons and electrons, right? There is some neutrinos in there, and there's some other particles in there. And so they will slightly alter the speed of sound in the medium. But nevertheless, we get sort of a 1.5% accuracy on this particular scale. Okay, and that is again the scale that a wave can maximally have traveled, i.e. the biggest wave I can make at the time of the CMB. Okay, so the question is, can we see that scale in the CMB? And indeed we can. And what you see here is what's called a power spectrum. Okay, so if I take one of the images of the fluctuation in the CMB, and I calculate a quantity that is called the power, and that is simply what is the likelihood of finding a hotspot at some distance from any other hotspot. Okay, so I take one hotspot, I count all hotspots around it as a function of distance, and I take the next hotspot, I count all hotspots around it as a function of distance, and I add all of those up and I square my result. Okay, that is the power spectrum. And you see that indeed, this weird quantity L that is plotted down there is related to inverse distance. Large distances are to the left at small l, and small distances are to the right with large L. That's a technicality. And you see that indeed the largest peak that I have, I can associate that with a scale of 143 megaparsecs. Okay. Now, what is so interesting about that? The thing that is so interesting about that is because that is an absolute scale, right? That is a distance, a size on the sky that I know in physical units, in megaparsecs. And I can relate that size to an apparent size on the sky. I can just measure how big that scale looks to me on the sky and associate that with how big it is in physical units, okay? So that's like having a yardstick at a distance of whatever it is, 12 gigaparsecs or whatever, or something like that, okay? So that'll become useful in a second. So now what happens with this density field after the microwave background decouples? Well, galaxies form in that same density field. They form out of the hydrogen and whatnot that we have there. And so they should know about these fluctuations later on, right? Where we have a little bit more stuff, we should get a bit more galaxies, and where we have a bit less stuff, we should have gotten fewer galaxies later on in the universe, okay? So these acoustic waves should also be seen in the galaxy distribution later on, in principle. And the interesting thing is that, again, the feature of 143 megaparsecs should also be there, right? And so now we can get a standard ruler, something that I know the physical scale of at any distance I want, okay? And with that, I can play a lot of games in a second, and we're going to do that. So the predictions of those features in the density field of galaxies imply a very deep understanding of the structure formation in the expanding universe, right? We really know what is going on if we can properly predict how this density field maps from just a very simple hydrogen plasma to galaxies, numbers of galaxies, okay? So people have looked at that, and here we have essentially the same plot as before, but now done with galaxies, okay? This is relatively nearby, so this is not at large redshifts. This is in the local universe, more or less. And what has been done here, just to make these waves a bit more apparent, is just divide by the large-scale structure of this plot, right? So we just took out the whole sort of large-scale curvature here. And again, the first wave that you can get, which is at a wave number of about, what, 0.08 or something like that, 0.07, again, corresponds to our 143 megaparsec sized ruler. And now we've held the ruler out somewhere at the CMB, and we've held the same ruler out sort of in the cosmic vicinity of the Milky Way. So that thing of known physical size seen at various distances can be used to map the expansion history of, and also the geometry of the universe. And how that happens is as follows. It really is the same as what you would do on the Earth if you wanted to figure out that you're actually living on a sphere. You can take a ruler and move it further and further away from you. And if you look at your globe that you have at home, you would see that what's parallel at the equator, i.e., let's take two lines of longitude. They are parallel at the equator, i.e., they have a fixed distance from one another. If that happens to be 1 hour of longitude, then they have a distance of 15 degrees. And if you take a ruler that size and you move it further to the North Pole, you'll see that suddenly, after a while, this ruler is bigger than the distance between the two lines of constant longitude. And that is an expression of exactly the positive curvature of the sphere. And that is exactly what we can do in the universe, okay? So if the universe is positive curvature, like at the example on the left-hand side here, then this ruler will look smaller than it should look to us if the universe were flat, which is the central diagram. By the way, if the universe is flat, then the ruler simply becomes smaller just with distance, right? It's twice the distance, half the size, okay? And in the negative curvature case, the ruler looks too big, right? It becomes smaller at a lesser rate than expected in a flat universe. And the same thing happens with the splotches in my cosmic microwave background, right? They can be more clustered in the case of a positively curved universe, and they are less clustered in the case of a negatively curved universe. And again, if you can do that at multiple distances, then you can also cover the case where the expansion rate actually, or the geometry even, actually changes with distance, right? You can map that step by step. Okay, and in principle, this is nothing different from what we do on the Earth to figure out that the Earth is curved, the surface of the Earth is curved. You can obviously also do that with a standard candle, and it's exactly the same experiment, right? A standard candle is something that you know the intrinsic luminosity of, and you're looking at how the apparent brightness, i.e. what you measure, changes with distance. So we would like to have geometric tests like these at every single distance, because we want to understand the whole expansion history and not just the beginning and the end point. The situation a few years ago when I wrote this talk for the first time was we had the CMB, then we had a long list of nothing, and then we had galaxies traveling nearby. These are the two plots that you have seen. And HETDEX is one of the experiments trying to fill in this big gap. And this is quite hard because to see these fluctuations in the galaxy number density, you need many, many, many galaxies. You need about 1 million galaxies to see anything, right? Or ideally more than 1 million galaxies to see these very small changes in galaxy numbers. Okay, so HETDEX is trying to do that at currently the largest distance, where people have tried to do this with galaxies. It also, at the same time as measuring the expansion rate, it measures the curvature of the universe at that point, right? i.e. we can eventually say whether the universe has always been flat or whether it had curvature at some point. And together with other experiments, it will fill in the expansion history over the past 12 billion years or so. And by the way, these experiments, although we haven't touched on that in particular yet, they're also sensitive to many other interesting cosmological measures. Some of them relating to inflation, Some of them related to the matter content compared to the dark matter content, i.e. the baryonic, compared to the dark matter content. For example, the way you get that, if you want to know, is you've seen that there is a number of peaks in these diagrams, not just the 143 megaparsec peaks, but there is peaks at smaller and smaller scales. And those are, of course, waves that have, have gone through more than one expansion and contraction cycle, like waves with smaller wavelengths, right? And the point is the following: dark matter is the dominant source of gravity. That's what pulls the wave in. And the pressure from the matter, i.e. the photons, is what pushes the wave back out. That's the restoring force. Okay, that's why we get oscillation. That's why we get wave propagation in the plasma. And so if you look at the largest wave, that's a wave that basically collapses, and the CMB decouples right when the wave reaches its maximum density. And that's it. It's the wave that traveled as far as it can go. And then it no longer can propagate because the photons are gone. The restoring force is gone, okay? And the next peak in the sequence is the wave that contracts and expands, and then the photons disappear. And the third one is a wave that contracts, expands, and contracts, and we let it go the third time it hit one of its peaks or troughs, right? And so the first peak, which is only contraction, measures the density of dark matter, essentially, the source of gravity. And the second peak measures the restoring force, which is essentially the photon density or the matter density, because the photons and matter are coupled before the CMB. And so the ratios of these peaks to each other and so forth give you a very, very rich data set to work on, trying to figure out the exact composition and the exact nature of the physical conditions. But that is not what we are concerned with today. I'm just saying that as an apropos for you to gain a bit better understanding of why these data sets are so incredibly rich and why they help us get measurements to, percent level precision in sort of matter densities and Hubble expansion rates and so forth. Okay, so this is the situation now, which is actually a lot better than it was just 10 years ago. We have the work of the Sloan Digital Sky Survey, which is BOSS and eBOSS, covering redshifts between 0 and about 2. There is some other surveys here and there, but BOSS is sort of the biggest and the most accurate one. Then we have the next generation of BOSS-like surveys, DESI, which is currently operating at Kitt Peak and will hopefully publish very soon. And then at the largest distances, there is HETDEX, which again, we are about halfway through the survey, a bit more than halfway through the survey. So results from this will come out in the next coming years. And then we have a lot of nothing again, but that is because there aren't any galaxies out there. And then there is the CMB, okay? But you can see from this diagram that we're now able to map the expansion history quite directly over a very large range in times, right? I've labeled redshift here, but really this is about 11 or so billion years, right? So the majority of the universe's history is mapped by these data sets. Okay, so what about before the CMB? So we've said that light cannot propagate past the CMB because the universe is opaque at that point. So we need to find other means to probe the universe before the age of the CMB. And we have multiple options. None of them are as direct yet as the data that I've shown you, but nevertheless, they shed light on the physical conditions early on in various ways. And among these are particle accelerators and what we know about particle physics from the lab. We now also have gravitational waves to look at. We do not see cosmological gravitational waves yet. The detectors are not sensitive enough, but we will eventually see gravitational waves whose origin is the very early universe. Actually, quantum fluctuations in the very early universe give off gravitational waves. Very small ones, but they give them off. And eventually we'll detect them. And then there is signatures in the data that act as relics of earlier events. For example, the power spectra that I showed you also contains signatures of inflation, for example. Inflation actually modifies the primordial power spectrum just very slightly by a few percent, and we can measure things like that. Another alternative to look at before the CMB is the Big Bang nucleosynthesis, and I'm going to talk about that just because this is a very mature one. And so again, this is something that we know at percent level precision. And that is very early on, the universe is hot enough to essentially be a star, i.e. engage in fusion, nuclear fusion. And nuclear fusion is basically in the early universe is driven by a race. On the one hand side, the universe cools off very quickly, so our reaction rates are going down very rapidly, right? And so about minutes after the Big Bang, the universe is just cool enough for deuterium, if you want the lightest element or the lightest isotope past hydrogen to survive. But it is so it doesn't break up right away again by something fast hitting it. But the universe is still hot enough for fusion to keep on going. Deuterium has a chance to go through another step of fusion to form tritium or perhaps helium-3 or helium-4. Okay, so we start with a single proton that gets hit by a neutron. Those two fuse to deuterium. And then we have multiple avenues to either go to tritium if we catch another proton, or to helium if we catch another neutron. In that case, we get helium-3, and then yet another neutron would form helium-4, or we can also have a path from tritium to helium-4, and so forth. And the ratio that we are left with is determined exactly by the rate of cooling at that point in time and by the density at that point in time, i.e. again contains information about the expansion history during that very short period of a few minutes when primordial fusion happens. And we have a very, very good prediction, which is 75% hydrogen, 75% helium, and the rest is essentially marginal, right? Fractions of percentages. There you go. And here is one of these calculations. We're tracing, again, minutes after the Big Bang, where you can see the reaction rates and the formation of various elements. And you can see that the only ones relevant in the end are hydrogen and helium, and everything else is orders of magnitude below that. But nevertheless, we have extremely good predictions, even down to sort of levels of 10 to the minus 10 or so, where we find lithium or beryllium abundances. So if we can measure the abundance of beryllium or lithium, for example, we get very, very sensitive information about the exact expansion history and the exact temperatures during these few minutes, because obviously their abundances are very, very sensitive to the exact conditions. Okay, what happens even earlier on? Well, earlier on than that, we don't have don't even have protons yet. We only have quarks in various combinations, electrons, muons flying around, and light. Okay, and that happens, about up to about 100 seconds or so after the Big Bang, and we can go another step back in the history, about a fraction of a second after the Big Bang, where we get quark-gluon plasmas, and that is about as far as we can get with accelerators on the Earth, right? So accelerators on the Earth, the LHC, gets to energies of about 100 giga electron volt or so, and that is to the state of quark-gluon plasmas, which we have produced on the Earth, and their physics is directly applicable to the conditions in the early universe. So what we find out at the end of the day, that actually accelerators are pretty good telescopes. And they are a kind of telescope that can actually look beyond the limit imposed on light by the microwave background radiation. And indeed, by studying particle physics in the lab, we get a lot of data that is extremely useful for us in our attempts to understand the early universe pre-Big Bang nucleosynthesis even. Beyond that, we have very high energy cosmic rays that probe energies much higher than we can produce in accelerators today on the Earth. However, experimenting with them is a bit difficult because we just have to sit here on Earth and wait for one of these particles to hit the upper atmosphere, and look at all the chaos it creates, right? So again, we know some, but not that much. And beyond that, we come into a regime where most of our knowledge is theoretical. Although we do have some hints of inflation happening in the, again, in the power spectra of the matter distribution that I showed earlier, but we can't say exactly what models of inflation might have been actually realized in the early universe and whatnot. And so this talk being focused on sort of hard evidence tapers out at these distances. But we've reached a point at this stage where our knowledge of physics also comes to a limit. Because accelerators are not high enough in energy yet to get direct data. And also because at some point, gravity becomes important again. Gravity is not very important in particle-particle interactions, just because it's the weakest of the four fundamental forces, and it's the weakest by about 40 orders of magnitude. Okay, so it is infinitely weaker, if you want, than electromagnetism, and you can see that by jumping out of a plane. You'll see that the Earth accelerates you over many, many, many kilometers. You fall down, but then when you hit the ground only takes a fraction of an inch to slow you down again and stop you. And that is simply a reflection of the fact that electromagnetism, which is the force that your body will feel when it approaches the ground, is so much stronger than gravity is. Okay, and so it takes a while. Particles have to get really, really, really close to each other for gravity to again be the dominant force. And that regime where gravity again is important is called the Planck length. And that is about the same regime where we expect effects of not just classical gravity, but actually quantum gravity to become dominant. And we don't have a theory of quantum gravity. So what we can say is that whatever we say about the universe these days ends at about 10 to the minus 43 seconds after the Big Bang, right? We simply have no physics that describes what happens before that. And so, people that say, the Big Bang is a point of infinite density, it isn't, right? It is so only in classical general relativity, but that is simply the fact that general relativity is not the right theory to use at this point. It has to be quantum gravity. And the prediction of general relativity is just like the prediction of classical electrodynamics that says an electron should have infinite self-energy because it's a point mass. And just as much as that is not true, the same is not true about the general relativistic predictions about the first moments of the universe. Okay, so I want to end this with a few clarification. And those are the Big Bang, first of all, is simply the idea that the universe expanded and cooled from a hot, dense earlier state. There is overwhelming evidence that that is true. The Big Bang is not an event in space. It is really a moment in time, right? It happened everywhere in the universe at the same time. It is in classical physics a singularity of infinite density and curvature, which obviously means just our physical theory at that point breaks down. Now, the Big Bang is actually just shorthand for the hot, dense state approximately 14 billion years ago. It is not, or should not be taken to mean the event that created the universe. Because that event might have been the beginning of the universe, or it might not have been the beginning of the universe. We don't really know. What we can say is that if the Big Bang was the beginning, the universe certainly did not pop into existence at that moment, because there was nothing out of that moment, right? You can't pop into anything before time exists. It is better to simply say the Big Bang was the first moment in time. That is where time and space begin at the same time. There is no distinction between the two, okay? And finally, because there's nothing outside of the universe doesn't expand into anything. It simply is everything, right? Don't think of it as a ball a sphere, say, that is somehow suspended in 3D space and it expands into like a balloon, the balloon model, right? Where somebody tells you, look at the surface of a balloon, I can blow it up and look how it grows, and the galaxies go, they look like a Hubble law. That is only, this analogy only goes so far. And where it breaks down is the fact that we see the balloon expanding into our 3D space. And so naturally there's something outside this balloon. And that is not what happens with the universe. There's nothing outside the universe. It simply is everything there is. And the scale of the universe, everything in it is becoming more distant, right? But both space and time begin and end with that universe. Right. Questions?
Fantastic presentation, Dr. Drory. Thank you so much. It's just an absolutely, and I say awesome, not in the classical sense, but it is really an awesome thing to kind of ponder. We did have many questions that actually came up in the chat. We'll start off with Dan Roy. He had a few questions about H0. Dan, do you want to come off of mute and ask your questions to Dr. Drory?
Sure.
Dan, can you hear us okay? Okay, we're not hearing you. I don't know if anybody else is hearing Dan right now. I see you're off of mute, but we're not hearing you yet, Dan.
Cannot hear Dan.
No, okay. We'll come back to you, Dan, after just a bit. But we had another question from Blanca Behar. Blanca, do you want to come off of mute and ask your question?
Yes, let me. Yeah, I was wondering, because we have the law of conservation of energy, that the energy cannot neither be created nor destroyed, only converted from one energy to another. So my question is, then that means that the universe already existed of the matter or energy to created it?
So that's a very, very good question. And the answer to that, fascinatingly, is no. And the reason is, in general relativity, there is no conservation of energy. Okay, so energy on the largest scale of the scale of the universe is not conserved. Actually, it's a meaningless concept. And to understand why, we have to go back and see where conservation laws actually come from. Conservation laws in physics have a very deep relation with symmetries. And symmetries are things whereby some physical law doesn't change if we do something to it. One example is we could, for example, flip left and right. And if we have a physical law that doesn't change when we exchange left for right, then we say we have a symmetry in this law, right? Or another symmetry is if we rotate something, right? If I take your lab and I just rotate your lab 90 degrees, and physics in your lab remains the same, then the physics you are working with is symmetric under rotations. That's what we say, okay? And it turns out that there is a very deep connection between such symmetries and conservation laws. Namely, each symmetry has with it associated a conserved quantity. And the conserved quantities that you typically think of all have their origins in such symmetries. For example, the one we just talked about, rotation. Anytime your system is symmetric under rotations, angular momentum is conserved in that system. Anytime that you can translate the system in space, you will get conservation of momentum, i.e. conservation of momentum is a consequence of the fact that if you move your lab 1 mile to the left, your physics is not going to change. You'll do the same experiments, you'll get the same results, okay? Every time that is true, momentum is conserved, okay? If you can do the same in time, i.e. you can do your experiment tomorrow, and it will lead the same result as it did today, energy is conserved. Okay, so energy is time symmetry. Momentum is translation symmetry in space, and angular momentum conservation is rotational symmetry. And every other symmetry, every symmetry in particle physics has an origin like that. Okay, so now we've come to a point where we can understand actually why your statement isn't true, i.e. why energy is not conserved in the universe on very large scales. And that is simply because the universe yesterday does not look the same as the universe today. Time translation symmetry, the universe is not time translation symmetric. If I do my experiment tomorrow, it is different because the universe expanded a little bit, okay? And so on scales where general relativity is important, or scales on which the expansion of the universe is important, you have no energy conservation. Energy is a meaningless concept. You can assign any number you want. It doesn't matter. Okay, so you can say nothing about the total energy content of the universe. It's a meaningless quantity. You can just make up a number. It has no physical consequence.
Thank you.
All right, thank you for the question, Blanca. Dan is not able to get on, but he did ask if I could read his questions to you, Dr. Drory. The first one was H0 is within 10% now comparing to CMB to type 1a supernova, not 1%. What gives?
Yeah, so the Hubble number is a bit difficult in that sense that we do have couple of percent measurements. It's like 2 or 3%. But we have different measurements that disagree on sort of a 10% level, right? If you look at the cosmological measurements, they all give you one set of numbers, 68-ish or something like that. And if you look at the astrophysical measurements, the ones that are based on, say, the classical distance ladder, say the Cepheid measurements, they all give you values of about 72 or so. But you get 72 plus minus 1, and you get 68 plus minus 0.5, right? So each claim a precision that is percent level, but the accuracy obviously is not there in one of the two methods. The suspicious one is the astrophysics, because we have many, many different cosmological measurements that all agree. Not just the CMB, but also galaxy clusters and gravitational lensing measurements of the Hubble number and a few others. And so there must be something wrong with our understanding of how the Cepheid calibration exactly works, or the local distance ladder exactly works. But that's my bias as a cosmologist, right? If you talk to somebody who does that, they'll probably argue differently. But clearly there's something wrong with either measurement.
So thank you so much. Bill Spitzeri had a question. Bill, do you want to come off of mute and ask your question?
Well, I can ask it. Okay, Doctor, when you talk about the curvature of the universe, as you did earlier, is it even a valid question to ask what dimension it is curving into?
No, it is not, because it's not curving into any dimension. It is simply curved, right? So, and by that, I mean something very simple. I mean by that, if you did a measurement where you took 2 points and you measured the distance between them, and then you applied, say, so let's say you have 2 points, you just walk from one point to the next, in a straight line. You count your steps, okay? You get some number of steps, let's say whatever. And then you walk, instead of walking straight, you walk such that you make a right angle triangle. So you walk a little bit to the right, and then you walk towards your second point. Well, can you count the steps now? And you say, well, that's like a triangle. It's a right angle triangle. So Pythagoras should hold. And you do that calculation, you find out that it actually doesn't hold. Okay, so these two distances don't look the same as they do when you do the same experiment on the surface of your desk. That is what I can say about curvature. There is no dimension involved in that. It is simply the fact that distances, and hence luminosity as a function of distance, or apparent size as a function of distance, do not behave like they do in regular 3D space.
So are you talking about curvature of space-time then?
Yes.
Got it. Thank you.
Okay, thanks for the question, Bill. And we had another question from Don Selly. Don, do you want to come off of mute and ask your question?
Sure. I think Dr. Drory answered a little bit of it already. My question was about the Hubble tension, and you already addressed that at one level. But my question really results from the fact, if it's not really just a measurement errors like you said, is it perhaps an effect? You had the one slide where you showed the universe was homogeneous, but not isotropic, but not homogeneous, right? It kind of occurred to me when I was looking at that. Well, the astrophysics way of measuring, if the universe isn't homogeneous, you might get different measurements across bigger sections of space. Is that a valid effect? Is anybody looking at that sort of thing?
Yeah, that is one of the explanations that people have suggested, is that in fact we just live in an underdense region, and hence if you do very local measurements of the Hubble law, or you look at Cepheids in very nearby galaxies, you see that underdensity, and that just means that the local neighborhood behaves like a universe that is slightly less dense, or expands a little bit faster because there's less matter pulling it together, right? And hence we measure a slightly bigger Hubble number. That is indeed a possibility.
Yeah, so compared to the CMB measurements,
Exactly.
which are distance measurements, it's maybe a little, maybe that's where the tension's coming from.
Yeah, or even from the local cosmological measurements, which probe much bigger volumes.
Okay.
Because they look at millions of galaxies rather than 20.
Yeah.
Right. And so that could be.
Okay. Thank you.
All right, thanks for the question, Don. I wanted to see, Dr. Drory, are you okay if we take one or two more questions?
Absolutely.
Okay, I wanted to see if anybody had a question that they didn't put in chat, but if they wanted to ask that now, they could come off of mute and ask that of Dr. Drory himself.
I'll ask. So tell me about the difference between the fascinating things that you're discovering versus getting all the data. Is one tedious and the other is amazing?
They're both tedious and they're both amazing, I think. Gathering the data is very tedious. Working out the theory is just as tedious. There's a lot of people with very big computers working on very, very complicated codes, trying to figure out exactly how things work theoretically. So I think, yeah, I think both are at the same time tedious and quite amazing.
Great question. Thank you, Debbie. And one more question. Does anybody want to ask a question that they have this evening of Dr. Drory before we wrap up? Okay, there was one question that Dan Roy did have. He said, will James Webb Space Telescope not help complete the map of the expansion earlier?
James Webb, I don't think so. James Webb is not an instrument to do surveys of millions of objects.
Okay.
It doesn't have the right instrumentation to do that kind of work. It will certainly help with many other things. It will do supernovae, for example, and so it'll certainly help with the supernova-based measurements of the expansion rate and so forth. But it's not in this particular, not with the power spectrum.
Okay. Well, thank you so much, Dr. Drory, for, again, a wonderful presentation. I'm sure many of us are just barely hanging on in terms of our understanding of what's happening here, but it's fascinating nonetheless. And I really appreciate your time and spending your evening with us to talk about these things. These are absolutely fascinating subjects. So yeah, thank you so much. And what I'll do here is share my desktop just to kind of wrap things up here. Just wanted to say again, Dr. Drory, thank you very much. We will have this recording available for anybody who wants to come back and rewatch it. And for those who want to follow what you're doing, is there a way that they could follow you on social media or perhaps on the web and things like that, Dr. Drory?
I don't do social media myself, but
probably not a bad thing.
You can follow HETDEX and you can follow, the Department of Astronomy here. And I've seen you're going to a star party out there at McDonald, so you're going to enjoy that. That's wonderful. The star parties are great. Yeah.
Absolutely. And I believe at that Texas Star Party, they're trying to make an arrangement so where we could all visit the McDonald Observatory and have an evening at one of the telescopes as well. So that'll be a fantastic thing. And hopefully, if the timing works out and you're there, we'll have an opportunity to say hello in person. So, but thank you again very much for this wonderful presentation. I just wanted to say before we wrap up that our next month's meetings are going to be on March 2nd for the novice meeting, March 3rd for the general meeting. If you have any questions about what we're doing as a club, you can visit us at astronomyhouston.org. If you are on social media, like Dr. Drory, and you want to follow us on any of these social media platforms, you could do so at those different platforms that I have listed there. This meeting will be recorded and placed on our YouTube channel, so please give us a follow there. And lastly, if you have any questions about anything happening with the club, you can always send us an email at info@astronomyhouston.org. So again, I just wanted to extend my gratitude to Dr. Drory for taking the time to present to us tonight and give us a wonderful presentation. And we look forward to seeing all the wonderful things that he and the team over at the University of Texas McDonald Observatory are going to be doing to help us understand this cosmos that we live in. So thank you all very much. And I hope to see you all soon. Have a great time and stay safe.
Thanks so
Good night.
much.